Welcome back. In previous videos, we studied infinite series and explored several important convergence tests. In this video, we begin a very important new topic called alternating series. Alternating series are series whose terms change sign repeatedly. Positive, negative, and so on. This series appears frequently across mathematics, physics, engineering, and numerical approximations. In this lesson, we will learn exactly what alternating series are, how to determine whether they converge, and how to estimate their errors. Look at the famous example on the left side of the slide, the alternating harmonic series. Written out, it looks like this: 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5 minus, and so on. Alternating series are extremely important because these shifting signs can completely change how a series behaves. For example, we already know that the standard harmonic series diverges. But the moment we alternate the signs, the series converges. This happens because the alternating positive and negative terms cause a partial cancellation, which is the driving force behind in the convergence. If you look at the partial sums table on the right, you can see these concepts in action. Notice how the sums bounce back and forth. Our first partial sum, S1, is 1. Then S2 drops to 0.5. S3 goes back up to 0.8333, and so on. As highlighted at the bottom of the slide, these partial sums oscillate above and below a specific numbers, getting closer and closer to a fixed value with every single term we add. This bouncing behavior strongly suggests convergence. But how do we prove this mathematically? For that, we need a formal test. To prove convergence rigorously, we use the alternating series test, also known as the Leibniz Test. This test gives us 3 straightforward conditions under which an alternating series is guaranteed to converge. First, the terms a sub n must be strictly positive. Remember, the alternating sign comes entirely from the power of -1. Second, the sequence of the terms must be decreasing, meaning a sub n plus 1 is less than or equal to a sub n for all n. And third, the limit of a sub n as n approaches infinity must equal 0. If all 3 conditions are satisfied, then the alternating series converges. But let's pause for an important remark on the right side of the slide. Students often make the mistakes of assuming that if the limit is 0, the series automatically converges. Be careful. The condition that the terms go to 0 is necessary, but it is not sufficient by itself. We absolutely must also show that the terms are steadily decreasing, keeping that in mind as we look at the sum example. Let's put the test to work with 2 examples. In example 1, we formally test our alternating harmonic series where a sub n equal 1 over n. Let's check our 3 conditions. A sub n is clearly greater than 0 for all n. Next, a sub n plus 1 is less than or equal to a sub n, so it is steadily decreasing. And finally, the limit as n goes to infinity is exactly 0. All 3 check marks are hit. Therefore, by the alternating series test, the series converges. Now, let's look at example 2. The summation of negative 1 to the power of n times n over n plus 1. Here, our a sub n is n over n plus 1. While the terms are positive, notice what happens when we check the limit. The limit of n over n plus 1 as n approaches infinity is 1, which is not 0. Because this third condition fails, the sequence of terms does not vanish at infinity. Therefore, the test fails, and the series diverges immediately by the divergence test. Our key takeaway here is vital. Alternating signs alone do not guarantee convergence. You must satisfy all three results. One of the most beautiful and practical properties of alternating series is how easily we can estimate their errors. The error estimation theorem states that if an alternating series converges by the alternating series test and we decide to approximate its exact sum S by stopping after n term, the absolute value of our remainder or error is strictly less than the magnitude of the very next term a sub plus 1. The error is bounded by the first neglected term. Let's look at the approximation example on the right. Suppose we want to approximate the value of our alternating harmonic series using just the first four terms. Our fourth partial sum S4 gives us approximation 0.5833. The very next term in magnitude is a sub 5, which is 1/5 or 0.2. According to our theorem, the absolute error of our approximation is guaranteed to be less than 0.2. This means the true exactly value of infinite series lies safely within the interval of 0.5833 plus or minus 0.2. As you can see at the bottom, this property makes alternating series incredibly useful for numerical approximation. The more term you calculate, the smaller your error bound becomes, and the better your approximation gets. Because of this predictable error bound, alternating series are fundamental building block in computational science. They form the backbone of Taylor series approximations, power advanced engineering computations, stabilize physics simulation models, and drive the high precision computer algorithms we rely on every day. To wrap up today's lesson, we learned what alternating series are, how to rigorously test their convergence using the Leibniz test, and how to effortlessly calculate their approximation errors. In our next video, we will build directly on this by studying absolute convergence and conditional convergence, topics that introduce some of the most surprising and important ideas in the entire study of infinite series. Thank you so much for watching. If you find this breakdown helpful, please give the video a like, drop a comment if you have any question, and subscribe to the channel to catch our next lecture. See you in the next video.